investigate the history of the oceans by exploring the materials that have been left behind on the seafloor.
That is Katherine Allen, better known as Kat, who is an assistant professor of Earth and Climate Science at the University of Maine, who also works with the Climate Change Institute, doing a pretty good job of explaining the essence of what she does. I'm Ron Lisnett, and this is the Maine Question podcast. If you were to go about trying to explore the history of our oceans, it may not occur to you to dig up a bunch of mud from the seafloor and see what's inside all that muck. But that is where Kat and her team go to reconstruct the history of the ocean. The shells and creatures, dust from the land, and many other things can tell a story that dates back many thousands of years. It's a type of research that involves some detective work, as all research does, but it combines that work with adventure on the high seas. As you can imagine, pulling up mud from the bottom of the sea many hundreds or thousands of feet down is no small feat. So why go through all this effort? Well, the waters that cover 2/3 of our planet are a dominant force in our weather and climate, storing heat and carbon, among other things. Studying this history is one of the ways to help predict what will happen to our oceans in the future, and ultimately, to us. Kat and her team had a major cruise this summer in the Gulf of Maine, which is one of the bodies of water she focuses on. We caught up with her as all that mud is starting to be processed and analyzed for the stories it contains. Just wanted to take you back to, I don't know, maybe 7th, 8th, 9th grade. You're sitting in a science class as a younger version of you, and someone told you you're going to make your living in large part by playing with mud. What would you have thought at the time, do you think?
I would have been very excited and I think a little skeptical that was possible. But I had some great science teachers, K-12, and particularly a really awesome earth science teacher when I was in 9th grade. So I did, my interest in it was sparked pretty early.
When you break down what it is exactly that you do to its essence, how would you describe that?
I investigate the history of the oceans by exploring the materials that have been left behind on the seafloor.
That's pretty succinct. So, as we talked about, the mud at the bottom of the Gulf of Maine or of any body of water contains all that information. How is it that that information is embedded in that mud and in what's inside that mud?
Sediments are fascinating, and in particular, what ends up on the seafloor is a combination of so many different materials, and each has its own history. On the seafloor, there are tiny shells made by organisms, and that's what I specialize in. But there's dust that's blown from the continents. There's gooey organic matter that's made by creatures that live in the ocean. There are geochemical processes that make concretions that build up on the seafloor. There are all kinds of wonderful things that are building up on the seafloor in different places for different reasons. And studying these can tell us a lot about the history of the oceans.
Tell us how you extract the history out of those items you're talking about.
My specialty is studying the composition of shells that are made by a type of organism called foraminifera. And these organisms build calcium carbonate shells. They're mostly calcium and carbonate, CO3, carbon and oxygen. That's dominantly what they're made of. That's very similar to a shell that you might pick up on the beach. However, if we look a little bit more closely into that composition of these tiny shells that foraminifera build, there are variations. So there are isotopic variations. So each element often consists of different isotopes. These are atoms that have the same number of protons but different numbers of neutrons. So they behave chemically very similarly, but their weight their mass is a little bit different. So they behave slightly differently in the environment. And so we can measure different carbon and oxygen isotope compositions in these shells. And that can tell us about the environments that the organisms were originally growing in. And we can also measure, what my particular specialty is looking at trace elements that are sort of accidentally incorporated into these shells. So mostly calcium is what's incorporated into calcium carbonate. However, there are small amounts of other elements that sneak in to the crystal lattice and into the shell, and the relative amounts of, say, magnesium that are built into the shell can tell us about the temperature at which that shell was formed. So one of the things I'm investigating in the Gulf of Maine right now is temperature. I'm really interested in the history of temperature, and the Gulf of Maine is warming, and we'd like to know more about the history of what's natural here, what happens on long time scales. So a key to past temperature, I can't go back in time with a time machine and stick a thermometer in the ocean. But I wish I could. Then I would have a whole different career. But instead, the next best thing is I measure the relative amounts of magnesium to calcium in these shells. The higher the temperature in which a foram grows, the more magnesium it ends up with in its shell. And this is what we call a proxy. This is something we can measure now that represents some past property.
If you measure today the amount of magnesium, you know what the relationship is. Then when you go back in time, you can use that same relationship to figure out how warm it was back then. Is that basically how it works?
Exactly. It's your secret decoder ring that you generate today. You figure out exactly what the relationship is in modern living specimens relative to the conditions they grew in. For example, one way to do this is by growing them in a laboratory. That's what I did for most of my PhD, was what we call culturing work. So I had live organisms in the lab, growing them in different temperature conditions, different water baths that we monitored, and then measured the composition of those shells afterwards. And different temperatures, different pH. We're interested in all different kinds of parameters, and there are different geochemical properties. It's not just magnesium. There's a whole wonderful suite of elements that we can use to tease out these different properties. So we can grow them in the lab to figure out what that relationship is. We can also look at modern sediments and modern ocean conditions to tease that out.
How do you tell from these mud cores and these shells and things inside the mud cores how old something is?
That is one of the trickiest things about my job. It really is, figuring out how old things are. It seems like a simple question, but that takes a lot of careful, hard work. And one way that paleoceanographers, people who study the history of the oceans, do this is by something called radiocarbon dating, which some people may have heard of. We can measure the relative amount of carbon-14, this particular isotope of carbon that decays at a known rate, to other carbon, stable carbon, and try to understand how long that piece of carbon-bearing material has been sitting on the seafloor. So whether it's a shell or a piece of wood, or usually it's a shell, and then estimate an age based on that. And that's one way. Another way is by stratigraphy, by looking at different types of organisms that we find and comparing it to what's known about when these creatures lived. So we can use what's called biostratigraphy. We can look at the different types of the different species that were around and get insight into the age of sediments that way as well.
And so with these mud cores that you're taking up from the bottom of the Gulf of Maine or whatever ocean you're studying, obviously the deeper you go, the older the material is.
It sounds obvious, but sometimes mud moves around, right? We have to be careful about where we take our sediment cores, and we do. The norm is to have older sediment on the bottom and younger on the top, but sometimes there's slumps and and movements, gravity flows and things like that. So we do have to investigate that assumption.
How big a core of mud are we talking about, and how old were some of the creatures at the bottom of it?
In this most recent expedition that I went on in the Gulf of Maine this summer, the longest core that we collected was 13 meters long. And although I'm not entirely sure of the age of the bottommost sediment, my estimate, based on its composition, would be somewhere around 16,000 years old. As far as paleoceanography as a field goes, what's possible, I mean, you can go back tens of millions of years and get cores that are an order of magnitude longer than the one that I collected. So the Gulf of Maine expedition was fairly recent as far to a geologist.
A blink of an eye for a geologist.
Yes, exactly.
Talk about that last expedition that you were on. This was this past summer of 2021. What's that like? What's the logistical challenge, and what's the adventure like of digging up these cores? You're out in the middle of the ocean. It's not a calm day on a calm body of water, I imagine. So what's it like out there?
I love it out there. Being out on the ocean every day is a little bit different, and you're never quite sure what you're going to pull up from the bottom of the ocean. And you have a clue, but it's always exciting to try to figure out the best place to core and then pull up a core and check it out and find out what you got. And the process is really interesting. I mean, we do our homework before the cruise and we get all the bathymetry and the maps, all the available information that we possibly can, and we go out there as prepared as we can be. But there's still a lot that's not known about the seafloor, and there's still a lot to explore out there. And so what we do is, when we're coring, on the ship, we will ping the seafloor. So we'll send down essentially sound waves. We'll send down signals that then bounce back up off the seafloor. And there are different frequencies that we send down. Some frequencies will penetrate deep into the sediment and bounce back off of layers that are buried. And then there are some higher energy frequencies we send back just to understand what the, sediment water interface is looking like. And using that information, we infer what's down there. Is it bedrock? Is it nice, soft, layered sediment? Is it messy sediment, that's had some reworking, or we try to figure that out. So it's we do some detective work on the ship as we're sort of driving over a site that we're interested in. Sometimes if you do sort of a grid, we call it mowing the lawn. You drive the ship over and then you take a turn and you mow the lawn and you try to get an idea of what's underneath you. And then we get the coring device ready. So it's a lot of work. There are these giant tubes with weight on the top, and we have to rig it up so that we can get it overboard and lower down to the seafloor and penetrate into those sediment layers and pull them back. And so it's a team effort. What it's like out there in any kind of weather. Sometimes it's beautiful and calm. Sometimes it's not, but you just come prepared. Everybody brings all their all-weather gear, and it takes a whole team of people to move the equipment, to make the decisions, to pull it back up, and then to cut the mud open when we get it on board. So it's a really exciting process, and it's just that thrill of discovery. You're the first person to see this material is really exciting.
How do you do with seasickness, and what are some of the biggest waves you've been in? Have you been in storms and such?
I've been in some storms. We were really lucky on this Gulf of Maine expedition. It was we had some heavy rain. We had some sort of sideways rain, a couple of cold days, and people were looking a little green around the edges a couple of days. But for the most part on this cruise, we were really lucky. I am fortunate in that I don't typically get seasick. I very rarely get seasick. The only time I can remember feeling a little nauseated was when I had a really big breakfast on a day that that wasn't a good idea, and generally I'm fine. So I feel fortunate, but there have been some big waves on some cruises that I've been on. Particularly, there was one from Barbados to Bermuda where we hit some heavy seas, but I enjoy it. I really like being out there. It reminds me of the fact that 2/3 of our planet is covered in water, and this is what most of our planet actually looks like. And I like being out there and remembering that and experiencing that.
Sounds like you picked the right line of work, I guess.
I think so. I'm a water person. I just love water.
Maybe talk a little bit about the Gulf of Maine, which I know is a focus area for you. What does the history look like there? What kinds of changes has the Gulf experienced over this time? You said, 17,000 years you can go back and start analyzing. And I'm sure before that and after that, the temperatures and the conditions were quite variable. What's the history of the Gulf of Maine look like? What does that tell you about the present or the future, if anything?
The Gulf of Maine is a really interesting area because during the last ice age, it was, to our knowledge, full of ice. I mean, there was an ice sheet all the way out to the Northeast Channel. I mean, it went out to the Grand Banks. There's peat. There are terrestrial deposits way out there. So during the last glacial period, the Gulf of Maine was ice covered and ice filled, and then during the deglaciation, during the end, this period where the ice age was ending and ice was melting and the climate was changing really rapidly, there are records of the ice edge melting back progressively, closer and closer and closer to the modern day coast and beyond. And during that process, the sediments that were building up on the seafloor changed from being what you would find at the edge of an ice sheet, sort of coarse and poorly sorted and just all mixed up, and to progressively to finer grained, better sorted, more what we would call fully marine conditions. So that history can be extracted and has been by people who have been working in the Gulf of Maine for decades, longer than I have. I'm pretty new on the scene here. I'm learning a lot. I think that it's a really dynamic history that the Gulf of Maine has, and it responds very sensitively to changes in atmosphere and ocean circulation.
I've seen reports in the news that the Gulf of Maine is one of the fastest warming bodies of water in the world. Is that indeed accurate? And is there any definitive info on what human activity is doing to some of these trends?
The Gulf of Maine is warming rapidly. The relative rate depends on the time period that you're looking at specifically. And there was a study that looked at 20-ish year period that showed during that period the rate of warming in the Gulf of Maine was extremely fast compared to the rest of the ocean. And I think what we need to do moving forward is to keep building on that and keep monitoring the temperatures here and try to understand how it fits in with the rest of global changes that are happening. And so the Gulf of Maine is warming. It is a dynamic place. I mean, there are year to year and decade to decade changes that aren't just monotonically marching up a warmer and warmer slope. There are variations that we need to understand as well. So, for example, if there's a cooler year or even a cooler decade, that doesn't mean that the relationship to global warming isn't real. It just means that there are other factors influencing the Gulf of Maine temperature year to year as well.
You're part of the Climate Change Institute, and we know there's a lot of scientists looking at various ways that the climate has changed and is changing. How does your work fit into the bigger picture? Are the results that you find combined or correlated in any way with folks doing ice cores or, tree rings or other ways that the climate is being studied? Does this all sort of contribute to a bigger story?
Oh, absolutely. Yes. And it is so exciting to be part of this research community. I feel so lucky to have the colleagues that I do. There are a lot of connections between my work and the work of other members of the Climate Change Institute and the School of Earth and Climate Sciences. Bonnie Newsom is in the anthropology department here on campus. She's a coastal she's an archaeologist and has been studying coastal deposits, communities that have been living in Maine for thousands of years. And we are working to compare the ocean conditions that I'm reconstructing offshore with the composition of middens, so deposits that are left by human communities that contain fish bones and other records of what people were eating and how they were living. And I'm working with Bonnie to understand possible connections between changes in the environment, changes in the ocean, and what people were eating and how they were living. And that's we're still at the very beginning stages of that, but I'm really excited about it and working with her and her team. And I'm also very closely connected to the glacial geology group on campus. Not only am I married to one of them, but
That's as close as it gets, right?
That's about it. But also, it's a large group, and I talk and work with them frequently about these kinds of questions. And we are interested in the next couple of years in actually collaborating on comparing marine records of deglaciation of the end of the last ice age with changes that have been observed in the terrestrial environment on land by measuring the rate of recession of the ice, by measuring glacial landforms and dating them. And there are so many ways that we all connect. I'm never bored. In fact, I have the opposite problem.
I imagine the discussions at the dinner table can get interesting, right?
Yeah, mostly they're dominated by our 3-year-old at the moment, but yes, when we get a word in edgewise.
Yeah, right. So I heard you talk about this before, and it's a subject that has come up some, weather versus climate. I know you talked about the fact that what you study, or the effect of the ocean on the climate, is sometimes, or in the past, has not been considered as much in how weather is predicted or climate is predicted. But that is changing, and that is making weather forecasting more accurate. Can you talk about that?
Absolutely, yes. So in recent years, there's been an assessment of weather forecasting accuracy, and it turns out that the most accurate way to predict future weather conditions involves using a model that incorporates, you guessed it, the ocean. And that is, there's a tool, FV3, developed by Princeton's GFDL, Geophysical Fluid Dynamic Lab, that is currently the cornerstone of weather prediction, and that includes information inputs from on the ocean, on ocean conditions. And the development of that has been in some ways informed by longer term changes and climate. So climate and weather, climate is, in the simplest sense, is a long-term sort of average view of what we experience as day-to-day weather. It's weather is what we feel when we walk outside in the morning, and climate is the culmination, the synthesis of what happens on longer time scales, and sort of the average and then the range is how you can think of it, of conditions. And what's happening now is that the mean, the average, and then the range of variability is actually changing. That's what we talk about when we talk about climate change.
So these predictions are now more accurate because the effect of the ocean is being taken into account. Correct. What's next? Talk about missions coming up. I know, and you involve students in many of these treks out onto the ocean and such. What's on the horizon?
Absolutely. Students are involved in every part of what I do. They are essential. They do a lot of the important field work and lab work and synthesis of our results. They are absolutely the engine of this operation. And I feel really lucky to have an awesome student team, and students throughout my time here at UMaine have just been fabulous. What's next for us is working very hard to process all of the wonderful material that we got on this last cruise, this last research expedition. We brought home literally a ton of mud. I mean, a metric ton that needs to be studied now. And so what's next for us in the immediate future is we're going to spend a couple of years working through all of that, trying to understand it, getting radiocarbon dates, analyzing the chemistry of the shells, and piecing together what that might mean for long-term conditions here in the Gulf of Maine. But also, my lab group does a lot of work elsewhere. I've got a student working on cores that she collected in the Indian Ocean a couple of years ago, and we're working on materials from the New Zealand area, from South Pacific, and I'm also looking always as a researcher, thinking about my next expedition, where I want to go next. And that's still a work in progress. I'm still sorting that out. But a theme in my research is really understanding ocean atmosphere interactions. And the Southern Ocean is a really crucial place to study carbon going into the ocean, carbon leaving the ocean. Changes in circulation there have a major impact on global ocean chemistry and on global climate. So I'm quite drawn to the southern latitudes, but also the northern latitudes. This work here in the Gulf of Maine, the Arctic is a really dynamic place, and the North Atlantic is a very interesting part of the climate system. So I'm still sorting it out, but for now we are going to have a lot of lab work on our horizon here.
Well, enjoy your time playing with all your mud, and we appreciate you taking the time to share your story with us.
Absolutely, it was my pleasure.
Thanks for checking us out on the Maine Question podcast. We always appreciate the folks who tune us in. We can be found on Google and Apple Podcasts, Stitcher, Spotify, and SoundCloud, as well as UMaine's Facebook and YouTube pages. Questions? Comments? Drop us a note at mainequestion@maine.edu. This is Ron Lisnett. We'll catch you next time on the Maine Question.